Okay, perfect. So welcome everyone to another MCRN Colloquium. Today we're lucky to have Dr. Keisha Cook presenting today. She is an assistant professor at Clemson University, started there in August 2021. Before that, she was a postdoc at Tulane, and she got her PhD at the University of Alabama in May 2019 in applied mathematics and computational biology. So pretty impressive. Looking forward to this talk. She'll be speaking today on stochastic modeling of the Asian longhorned beetle infestation. And so with that, please go ahead.
Yeah, thank you for the invitation to the organizers for having me here. New network for me. So Emmanuel and I know each other from SciAm. Yeah, we've been in a couple cohorts together through SciAm. So excited to present for you all today. Now, yes, my background is in math biology, but more recently, because of some of the agent-based model and stochastic modeling projects that I've been working on, I met a collaborator in forestry at Clemson, and he was interested also in some agent-based models along with stochastic modeling. So we my research group, myself and a postdoc, began working on this project. Here are those collaborators. So Dave Coyle, he's in the Department of Forestry at Clemson here. And so they study Asian longhorn beetles, which is in that picture on the left side. And so this is studied primarily through USDA and APHIS, in short, forestry, Department of Agriculture, but interested in invasive species. And so this is one of the invasive species that they are interested in. Specifically, they had a lot of data available, and so this project was interesting because it's essentially looking at some data science, how to understand the data and how to make predictions, how to model that data, but also make predictions on what may happen in the future. Again, since these are invasive species, the goal is to eradicate them from areas or treat. And I'll talk a little bit more about that on the next page. But Dave Coyle is the, again, forestry faculty member. And then I have a postdoc, Ethan Doherty. Here, his background is forestry and agriculture, but he was interested in data science. So that's why we took him on as a postdoc on this project. And a math graduate, a master's student, Sam Klaus, and he is here again at Clemson in the School of Math and Stats. So these are the beetles that we study. So we took a trip down to Charleston, South Carolina, near the marshes. Specifically, these beetles like to infest maple trees. So really, you'll find these beetles in areas with heavy maple trees. So you'll see in some forward slides, those states, South Carolina, New York, Ohio, and Massachusetts are the states of interest where they have a lot of data. There's a lot of maple trees in those locations. And that data is consistent with this tree that you see here. So this is an example of one of the trees that we saw in Charleston, a picture that I took. And these holes that you see in the picture are about the size of a penny. And the process of a beetle, I guess the life process of a beetle, in the wintertime, the adult beetles will burrow themselves into the tree. So they'll make these holes and bury themselves inside. By the time summer comes next year, the upcoming summer, they will have laid eggs inside of the tree. As those larvae hatch and turn into larvae, they eat the trees from the inside out. And so that is causing the trees to die at the place at which they burrow inside. So if you were to look at this tree maybe a little bit later, yes, there are larvae inside of the tree now, but once they actually start to kill the tree from the inside out and eat that bark from the inside out, the tree will essentially crunch inward and then topple over, and then they know obviously that those are trees that are infested, but you can also look for trees with holes here that are infested. So this process takes about a year, of course. They obviously don't have people who are going out every day to find trees that are infested. The process of collecting this data is really sending out multiple surveyors into the forest. They typically go to areas where they found beetles previously and search trees nearby. They mark the trees that have holes or are already damaged, visibly damaged, and mark them with an orange band. And so there's a orange band around the trees, but then also this orange paint. So if it's marked with the paint, that means they're coming back soon with the company to cut down the trees. Otherwise, just you leave that orange string around it so that they will get to it sometime. So it's really not organized on the field data collection side, right? So it's a lot of scattered data. The data sheets are massive, but plenty of data to use to study how you can model the infestation, and meaning how can we see which trees will become infested next, make a prediction or probability model to say that these trees will probably become infested next. And there's a process of which they can treat the trees instead of treat the trees before they are infested by the beetles, instead of tearing down forests after all the trees are infested in that area. So this is one area that's highly infested. So you'll see a lot of down trees, but then also this is in Charleston, South Carolina, but you have the same type of data in Ohio, Massachusetts, New York, and South Carolina. This figure on the top left is Massachusetts. And one of the things that we future work is once we have this model published for round one, we hope to incorporate GIS data. So that is now looking at the areas where there's houses, where there's rivers, where there's, just things that will either inhibit or allow for infested trees to spread faster. So yeah, right. So that's what our data for Massachusetts looks like. So if I focus in on Massachusetts, I'm just going to talk about Massachusetts for today. It's the largest data set, but it also has the most years available in that data set. So they have data from 2008 to 2021. The newer data is issues with the newer data, but we have good data for the surveyors up till 2021. And so it will look something like this. You have trees, you have a data sheet that literally has the labels of all the trees, their latitude, longitude, coordinates, how old the tree is, the size of the tree, how many holes they saw. So the data sheets, again, are massive with a bunch of information. And I'll talk a little bit about the data points that we settled on to actually build the model. So the most important data points that are necessary for the model. But again, we want to simulate the spread of these AOB populations. In other words, the spread of the infested, the beetles infesting trees through spatial stochastic models. So really, we started thinking about this from the perspective of point distribution. So if we can study like the distribution of infested trees at a specific year, how that changes over time, and then make a prediction. So we use that in our model. So there aren't any published models in literature, but there is a model that was developed through the lab, one of Dave's collaborators' labs, and they used the following terms or equations for the probability of a tree becoming infested. So essentially taking all the trees that they see, and this is all the black points are trees in a forest in Massachusetts, I believe, just one small area, but letting the terms for the probability of a tree becoming infested be defined by the following. So distance being distance between trees that are infested and uninfested, and infested and infested. The density of the trees in that area where you see infestations occur. DBH, which is diameter at breast height. So that's relative to the size of the tree and age of the tree. And then a source term, which is based on the trees that are infested here what's the probability that the trees closer or farther away are going to become infested. So they call that a source pressure term. And then they have another term, mu. So these values, if you look at this document that they have in the lab, are primarily just chosen to model the spread. So if I were to watch this video, you'll see the red dots increase over time, but there's no, it's not inferred. So the values are not inferred from data. They're just selected to make the model work, essentially. So our goal was to come in and use the data to actually study how that probability of becoming infested can be inferred from the data that's actually out there. So we have a couple of different categories of how we're going to look at this infestation model. And so there are uninfested trees, which are most important. We want to know if these trees are becoming infested. There's also trees that are high risk that we consider. We consider this because the surveyors will say, oh, these trees are kind of close to a lot of infested trees. So we're going to cut down these trees so that they don't become infested and hopefully don't spread the infestation further. So with that thought process, we said we should probably also include a category of high risk. So these are trees that may become infested and may become removed prior to becoming infested. Also, there's infested trees because infested trees that are part of two different categories. So they're either detected or undetected. And so I mentioned that the surveyors go out into the forest and they literally walk around and look at the trees to determine if they're infested or not. And so you have millions of trees. You have some infested trees that you're going to miss. And so we have some probability that that the infested trees are detected or undetected, and the detected ones are the ones that will be removed in our model. So we want to consider all of these in our probability of becoming infested, and I'll talk a little bit more about what goes into that probability next. So we have I mentioned some of the data that's in those spreadsheets, but we specifically focus on the XY coordinates, the diameter at breast height, so DBH. Are beetles present, yes or no? It's literally yes or no column in their big spreadsheets. But we also incorporate something called a proximity matrix, which just takes into account the distance between infested trees and uninfested trees, but it gives us a big table of distances for every point that you have in that space. So think of a two-dimensional space with about 1 million points in that Massachusetts data set. If you were thinking back to that plot that I showed a couple slides ago, a short matrix means that we're considering these being infested possibly next. A short matrix has to do with the fact that the surveyors choose a radius to survey in based on an infested tree population. A longer matrix takes into account a larger radius, one that maybe the surveyors have not actually surveyed yet, but we can do that in our model and make predictions essentially. But also we can say maybe you should survey a larger radius so that you capture more infested trees or can treat the trees in that larger radius. But then there's also the detection matrix as well. That is a proximity matrix. And this has to do with the trees that are infested specifically. Will they become detected or not? And again, that has to do with the surveyor's thought process and when they go collect data. Right. So with that probability of a tree becoming infested, I mentioned the terms, but I want to break them down now, how we use the data to do so. So we're using a G function, and this G function is a proportion function. So it's a proportion of trees that fall within a radius of another tree type. And so we look at that between how far the distance between infested trees and infested trees. That's important to tell us more about how many infested trees are really in that area within that radius. And then also uninfested and infested trees. And that is also important because we want to know how many of these infested trees are actually are close enough to the uninfested trees to become infested. And so we can look at this this from a data sheet and fit it to a curve. And so from that proportion, we have the following two equations, and we can then use this as one of the probability terms in that probability equation for becoming infested. So a proportion here, so the probability of becoming infested, so just rewritten in terms of the probability, but the figure to the right is actually from the data itself. And we choose a distance of 1,000 because that is the literal length in meters that the surveyors will survey when they go out. They'll select 1,000, a survey area with a radius of 1,000 meters. So I also mentioned the diameter, the DBH term, and this has to do with, again, the size of the tree. And so we can take two proportions and look at these according to the different category of the tree. So the number of infested trees, again, this is all from the data. So if we look at the number of infested trees that are in a specific bin number, so we have a bunch of trees and we just look at their sizes. So look at the sizes in that bin and divide by the total number of infested trees. Also, we can do that by the other uninfested category. So look at the sizes of the trees that are uninfested within that bin, and then we can scale that to a probability of a tree being infested based on its size. So we have a nice formula for this as well, again, coming from the data that has been collected. The source pressure term, again, the source pressure has to do with really it's density based. So how strong of a pressure are you giving if you have a lot of infested trees in one area? How will that affect trees that are nearby? Right? So from this, I mentioned the stochastic process, so we can really use two-dimensional Poisson, non-homogeneous Poisson process to think about this, and essentially extract the lambda value, so Poisson process, but the lambda value, which gives us the density of the categorized trees within a small area. So we can look at all the points. Again, this is everything from Massachusetts from 2008 to 2021, but this is just to show that if I were to look at this over all that data at once, not per year yet, but just all at once, I can see where it's more dense. And in our model, we're actually looking at this per year. So yes. And so you can extract the lambda term here, and the lambda is incorporated in our SP score. And so source pressure SP, but this score is the value that's used in the SP pressure term, the source pressure term that we use again in that probability of a tree becoming infested. So based on the source pressure of the area that the tree is in currently, an uninfested tree is in currently. And so here explains that a little bit more. So we have our SP score. From the SP score, we can put this in the same bins, similar to how we did previously. We have, again, 1 million trees, so we can compute each tree's SP score and bin them, look at them with respect to infested and uninfested, and this would give us the probability of a tree becoming infested based on its SP score. Again, this has to do with the density at which a tree is in your space currently. And so those three terms come together again for the probability of a tree becoming infested. That is one step in the model, but of course, since we are looking at what happens over time, and every time step, trees are becoming infested, in different time steps, trees are also being surveyed. So we again, I didn't think I said this yet, but the process of the beetle lifespan, the beetle life cycle is about a year. So they have their data sheets, one per year. Now, did they collect all that data all at the same time? No, they did not. But all of their data sheets are labeled by year. So any data that was collected in 2021 could have been any time that year. But we treat that as 2021 data. So we're going to let our time steps be 1 year. And so we have surveying happening once a year. We have survey, at least once a year. And then removing trees is also happening at every time step as well in our model. And so we would have a percentage, or essentially a probability based on, for surveying at least, you have to find detected infested trees. And then for removing, these are also related to your detected infested, but you can remove trees that are not, that are either high risk, remember I mentioned that before, and infested trees. So infested trees in both categories, either undetected or detected. So removals, again, are happening with respect to 3 different categories of trees. So I want to show a little bit of the simulation, what it looks like. Again, this is Massachusetts. This is Massachusetts data, but you have your green points that are uninfested at time 0. It does start over. Now it started back at the beginning. And red is just infested. Just infested right here. I didn't want to overwhelm with a lot of the other categories right now, but uninfested for now. One of the questions from the surveyors is really, can we use the model to suggest different management strategies, meaning do we need to go out and survey more often? Do we need to improve the survey radius? Do we just stick with 100 meters every time? Yes or no? And those are the type of things that we are working on with the model now to answer the questions. So now that the model is working with respect to its probability of infestation and removal and survey and things like that, now looking at comparing this to the data, comparing the model to the data, but also being able to answer the questions. So do you see unmanaged on the left-hand side? The unmanaged, again, means we're not really going out and surveying as much as you should. So you just see this infestation blow up pretty fast. By tick 2020, almost all of the trees are infested. But if we are managing that with specific survey instructions, removal instructions, then you'll see the infestation is growing and shrinking. You'll see this is at the end of the simulation on the right-hand side. It's about to start over in a second. Starting over now. The infestation is growing and shrinking over time. Again, this has to do with the trees that are either becoming infested, but also how often are we going to survey and remove the infested trees. So that follows here as well. So that was unmanaged versus managed. But then we can also, again, if we just focus on one of those strategies, for instance, surveying, then you can just see the difference with if you keep detections the same, if you keep infestations the same, everything is the same except for the information that has to do with surveying. And again, this has to do with how the surveyors are going out and figuring out which trees are infested or uninfested. So little surveying on the left-hand side. So that's what you saw previously with the unmanaged side. But if we increase the surveying strategy, then we can see that infestation not spreading as much in that area. So I mentioned that we do have a lot of data, so not only focusing on what the model is doing, but can we say that this is a good model to match the data that is currently available? And so from the surveyors and field scientists, I should say, they noted 5 variables that are most important for that model calibration. And these are also go into what we have in the model what we consider input, right? So we can input a survey area radius, also the rate at which you're detecting infestation. So that has to do with that survey. So are we doing that faster or slower within that year? The beetle spread radius. This is also has to do with how far the beetles can travel based on the spatial information of the trees. How far are the trees from each other? The number of survey events that we want to do, and then also the number of tree removal events as well. So because this is an agent-based model, it's stochastic, time series, all of the above. One of the techniques that's good for this specifically is history matching, along with approximate Bayesian computation. So this allows you to look at, so instead of being able to write out the likelihood functions and the posterior from that, develop what the posterior distribution would be, which would tell us the estimated values of each of these parameters, these 5 parameters. We cannot write a likelihood function. And so we are essentially testing that parameter space, and we're just getting closer and closer to those values that would give us a good estimate of the population of one of the populations, let's just say infested population over time. And so to do so, we need to use history matching, again, to test the bounds of that parameter space for each of them. But then the ABC method is actually what's saying what is the best parameter value for each of these 5 variables. And so here's a little model of what the history matching is doing here. This will be in our first paper. So we're trying to have this done by December and submit it. We're working on this model calibration and validation side now, but this is a little schematic from this paper that we are using to figure out what our parameters are. But again, we have our initial parameter space. We treat this as our ideas from the surveyors and the field data scientists, how they collect their data, all of the above. So that's our initial parameter space. And we can sample from that parameter space. We can look at the ensemble variance and model discrepancy. What is that? Plugging in those parameters, testing them out, getting our output for the time series of the different populations, comparing them. How well do they match the data? Calculate implausibility. This has to do with how far those time series are from each other. Is it really far from actuality, or is it close? So we can choose a value for implausibility. And then from there, pick a new parameter space and test again. And then this leads to the ABC model, which is in the second box below, which actually looks at the correctness of the parameter with respect to the plausible values that we found in the history matching section. So this will give us our posterior distribution, in other words, the best estimate for those 5 variables on the previous slide. Yeah.
So in your parameters that you're estimating, I didn't see the lambda from the Poisson PDF. Is that also included in your parameter space?
No, because that's directly computable. That's literally from the data.
So then are you using a maximum likelihood estimate for it, or
no,
how are you getting?
ABC does not require that. So that's why, because you can't write a likelihood function based on what we have. Yeah. So it takes, yeah. So if I go back to this one, this is the field data is the line at the bottom. And while this looks far apart, this is actually better than previously, because again, there's 1 million points and we're getting closer to reality here. But you sample from your parameter space, meaning you choose a value from that, a good estimate value from each of those 5 variables, plug them into the model, and you run the model to get this curve. Once you have this simulation curve, you're comparing it to the field data. So we have a error term in there to say that if this is those 5 parameters that we chose are plausible if the distance between these curves is within that specific error band. And so this is just to show we have 100 or so, I think it's like 1,000 or so simulations here in the simulated data. The black line through it is the average, but this is to show where the field data is with respect to that simulation. So you don't need, for ABC methods, you don't need a maximum likelihood. You don't need a likelihood function at all. You don't need to write out any PDFs. You're testing with respect to whatever your model output is. Yeah.
Thank you.
Yeah. And so, yeah, so in the last couple of slides, I just want to show a little bit of the Shiny app. So the goal for, again, publishing this in December, but also along with the Shiny app. So we're doing this in R, and from the user side, you would be able to choose your parameters. So for instance, let's say there's another, I don't know, let's say there's maple trees in Tennessee. It's probably not, there's none in Tennessee, but let's just say that. Let's say we have some new data arrive in Tennessee and we wanted to see what this survey would be. So you would import or upload here your data, CSV. There are instructions to tell you, which categories you need, but I mentioned that on previously. That's like your latitude, longitude positions, are beetles present, yes or no, size of the tree, like all that's normal data that would have been collected. So once all of that is in your CSV, you can upload it here, process it through our filters to make sure it's all correct. Put in your radii of upper and lower radius. Again, this is for the two survey radius that I mentioned. You can upload you can calculate the diameter at breast height table to tell you how your probability of becoming infested is related to the size of the tree. Press this button, it will begin that process. If you already did it once, you can just upload it so that you can, you don't have to start over. Same for the nearest neighbor calculator for that distance term. And then there's some other buttons. Again, this is just a snapshot of some of it. You can also then, in the next tab, you can run the simulation. So the simulation needs a proximity matrix, which is the distances between all the different categories of the trees. So that will run first. You do have to choose, all your simulation setup here. You can choose it however you'd like. And then run the simulation. And after you run the simulation, you can choose which output you have. So the output would look like the following. For instance, for the screenshot purposes, I just put different color categories, but red trees were uninfested, red trees were infested trees, green trees, uninfested over time. And I ran this simulation for 30 years. Purple trees over time. And so all you need is a data set of initial data. And you need a data, in that initial data, it should say, let's say 1,000 trees. It needs to label which ones are uninfested and infested at that time. And so then it will take your model from there and make predictions on what happens later on. So I think purple is high risk. So yeah, that is all I have for today. Thank you.
Awesome. Thank you very much. Find my clapping emoji there. I'll thank our speaker. So that was really interesting. I guess we certainly have time for some questions. If anybody had any, please feel free.
So is there anything they can do? I mean, if you predict that these, that these beetles are going to infest a certain group of trees, is there something they can do to manage that, or?
Oh yeah, so they manage it by either doing more surveys, so sending out more people to label the trees, but from there, when they're labeled, they then have to go through the Department of Agriculture to get the trucks to come cut the trees down.
So they cut them down, is basically what they do. Yeah.
Or they treat them. So the other one
They
is
treat them. Okay.
So if they can, so the goal for this is to hopefully have less trees being cut down and be able to make predictions on, like, in the next year, these trees should become infested. If they're not already infested, let's go ahead and treat all the trees within this specific radius. so that we don't have an infestation that blows up.
Okay.
Yeah.
Good.
There's two options, but right now they primarily just cut down trees.
We just cut them down. Yeah. Good.
Any other questions?
So I don't know much about agent-based modeling. I mean, I do, and I think most of us here do sort of more like dynamical systems, differential equations modeling. So are there any such models of this type of thing, or?
Just what they, and not based on data either. So the models are really just simulation based. And so like I mentioned here in this slide, this is just from their lab, and this is what their lab has just been using. And they have estimates for what these values should be. Usually it's like an average, like this DBH term is an average. They say average tree size or tree age and things like that. But this model, I think they did this and they used MATLAB for this, but it's not based on data. It's just based on estimates. There's some values for like this E2, B, the gamma and the C2, the alpha, like all those parameters, those were all just parameters that they used to say, oh, if you look at the video, the GIF of the spread, it looks like it's something that's realistic. And so there wasn't, evidence to back up why they chose those parameters. And so that's where we're coming
in. Okay.
Yeah.
Any other questions? If not, I have kind of a more abstract one, I guess.
Yeah.
So that I guess these beetles can certainly kill the maple trees.
Mm-hmm. Yeah.
In which case they would become dry and essentially fire fuel. So I wonder, can they spread quickly enough in an unmanaged situation to where you might increase the probability of a wildfire in area with a dense maple tree? Do you think that's, or do they move a little bit slower than?
Yeah, we haven't thought about that with respect to the fire, but they can spread. Yeah, they can spread pretty fast, especially if there's a lot of beetles in that area. But multiple beetles can infest a tree. So if there's just a lot of beetles in that area, then yes, they can spread pretty fast. In Charleston, there was what they call it one of the famous cases, because Charleston, it's on the water, and they have like small islands. There's also maple trees. So like there's one, can't remember the island, but the name of it. I put that picture up here, but anyway, we were walking to it on the other side of this picture after the forest. The island is probably like it's maybe like 100 meters wide. It's just a small island, and it's covered with maple trees. It's like a little walking path, and they had that isolated infestation there, and they were able to like really study that and how fast it spread because it was isolated, and there was nothing coming in. But that's the only isolated incident that they had.
Okay.
Yeah, so that could really, if we were to use that, that could tell us more information about how fast how fast the beetles move from one tree to another. Yeah.
Okay. Yeah, that's really interesting, because I've been learning more about fire, and this fuel moisture content in the available fuel is a very key parameter, and so it's just interesting to think about what else that I would have never thought about maybe affecting those values.
Yeah.
Okay, very cool.
I have a question. Would you mind going back to the slide you were on just previously with the model? And sorry, you may have already answered this, but so you've got some things like gamma, B2 parameters essentially, and my understanding is those are provided to you in this reference. Is that correct? Like you?
Oh yeah. So this is what the lab is using. So this is not even a reference. This is just like
Just what the lab is using.
This was the lab before we were involved.
And have you looked at all, like if you switch those parameters a little bit, if it if it seems to match better, like if there's if you could model even more accurately by.
But remember, this is not based on data. There's nothing to match it to. This simulation is strictly they simulated a bunch of the black points here are infested trees, and the red points are, this is like strictly a simulation. This is not based on data at all.
But you do have data that you're working with
Now, yeah.
right?
So this is our model has to do with like these. So we developed that model. We used the
You didn't use that other model at all then.
right. This was
Gotcha. Okay, sorry, I
Yeah.
missed that. My bad. Thank you.
yeah, this was the original.
I was thinking.
Started.
Yeah, I was thinking along the lines of like data simulation, but you aren't even using that at all. So gotcha. Thank you for that clarification.
Yeah. We used the idea to have a bunch of terms that lead into the probability of infestation, and we have all of them, but structured differently based on a data set, a real data set.
Cool. Thank you.
Your new model is what you're using in your shiny, right?
Yeah. So this slide again is just where the lab was before we were involved. Yeah.
Okay. Any other questions for Keisha? Okay. If not, I'll thank our speaker again, send some more clapping emojis, and thank you so much, Keisha. Very interesting talk, and see everybody next week.
Nice. Thank you for having me.
Great.
And thanks for inviting me.
Thank you.
Nice to meet you all.